Good morning. Alrighty, math folks. So today I want to, I want to recap some of the stuff that we did yesterday, the definitions of type 1 and type 2 improper integrals. And then I want to look at some kind of subtle things that maybe you thought about yesterday, Wednesday, and maybe you haven't thought about. I received a question or two via email that were very good. Really wonderful things for you to be thinking about, having to do with symmetries and improper integrals, specifically the type 2 integral that we worked at the end of class last time. But before I get into all of that stuff, I just want to remind you guys where we are, what we've been doing. This is the beginning of the second third of the course, which is by far the hardest part of the course, where we will talk about convergence. Let me flip you over to the .cam. So this is Calc 2. Today is the 26th. And we've been in section 7.8, which is on improper integrals. Sorry, I just got a text from my wife. I'm good. Oh. Oh yeah. Yeah, that looks nice. Where is that? Cool. All right. So the definitions. Type 1 integrals. Type 1 improper integrals. These are things like integral from a to infinity, f of x dx, or integral from negative infinity to a, f of x dx, where f is continuous. Right? This first guy we would define as the limit as some variable. I like to use r.
Hey, John, we don't see the screen.
No? Oh, shit. All right, that's not good. Thank you. All right, sorry, is that better?
Yeah, I see it.
Thank you. Sorry about that. So, we're in section 7.8 talking about improper integrals. I'm just going to go back over those definitions. Type 1 improper integrals. The function f that we're integrating is understood to be continuous. And if we're looking at the integral from a to infinity, so these are improper because the region over which we're integrating is infinitely long, either from some constant to infinity or from negative infinity up to some constant. This first guy I would define as the limit as some variable. I usually like r goes to infinity. The fan from this computer, so I brought my office computer home and it's one of these all-in-one things, and because I'm processing the video for my Calc 1 class right now, the fan is like spinning like a motherfucker, so that might be drowning me out a little bit. So I'll recap. So integral a to infinity is a type 1 improper integral because the interval over which we're integrating is infinitely long, and we define it to be the limit as r goes to infinity, integral a to r, f of x dx. And this other guy we define analogously as the limit as r goes to negative infinity, integral r to a, f of x dx. So these were type 1 integrals. Type 2 integrals here, f of x has an infinite discontinuity. at x equals a. And so those are integrals like from a to b of f of x dx. And here f has like a vertical asymptote at a. So we need to sneak up on that vertical asymptote. So this would be the limit as r approaches a from the right. Because I have this infinite discontinuity at my lower bound, I want to sneak up on that infinite discontinuity while staying within the interval AB. So I take the limit as r goes to this place where I've got a problem from the right, integral r to b, f of x dx, or I could have an integral like from b to a, f of x dx, where again I have an infinite discontinuity at a. And this guy I would define as the limit as r approaches a from the left, again because I want to stay within the interval AB and sneak up on that infinite discontinuity. And this would be integral b to r, f of x dx. In all of these, if the limit exists and is finite, we say the integral converges. And the way we use that language is we'd say that the integral converges to whatever that finite value is that the limit takes. Otherwise, we say the integral diverges. Okay, so these are the objects and the descriptors that go with those objects that we've been learning about lately. Good question. So the two dots before the equal sign, that's a colon equals. That means is defined to be equal to. So this little bit of notation, instead of just having an equals, we put the colon in front of it. That means is equal to by definition, or by definition is equal to. The reason for the limits, the reason we need all this careful treatment is because I cannot apply my fundamental theorem of calculus to shit like this because I can't build Riemann sums for it, but I can apply my fundamental theorem of calculus to shit like this because I can build Riemann sums for them. So you must first rewrite as a limit of a proper Riemann integral before you can do anything with these. And that notation step is very important. It is something that I'll be taking points off for if you skip on an exam. So I gotta be really, really picky about that. Remember to write the limit, remember to write the limit all the way through the problem. I know our hands will get a little bit sore, mine does too, but we're gonna be tough. We also had a theorem from last time called the comparison theorem. I won't go back through that. I don't want to write it all out again, but if you don't remember that, take a look back at our lecture from Wednesday. It says that if f is smaller than g and the integral of g is finite, then the integral of f is finite. And if f is smaller than g and the integral of f is infinite, then the integral of g is infinite. Above the new one. Here, I'll just leave this for a second. Yeah, so these are our definitions. This is what we're playing with. So today what I want to talk about are some of the kind of funny and weird things that show up here that you might not expect. When you play around with infinity, weird shit happens. That's going to be a theme that you will see showing up again and again over the next few weeks. When you play around with infinity, weird shit can happen. The type 2 example that we did at the end of class last time, where I had an infinite discontinuity, no kidding, no. Where I had an infinite discontinuity in the middle of my interval, represents an interesting example because the function was odd. it was an odd function, and I was integrating over a region symmetric about 0, and the value of the integral did come out to 0. And one of the good questions that I received, or fun questions that I received via email was, well, couldn't we have just made a symmetry argument to conclude that that integral was 0 right at the start? And the answer to that is no, but it's a subtle no. If you knew ahead of time that the integral converged, then you could make that argument. But remember, this was actually one of the questions from our test. That theorem that says if you integrate an odd function from negative a to a, you always get 0, really says if f is continuous on negative a to a, and you integrate negative a to a, you always get 0. Our function there was not continuous, right? It had an infinite discontinuity at 0. So I want to ask a kind of simpler version of that and explore this concept of convergence a little bit more. So this is a really general question here. What can be said about the integral from negative infinity to infinity of x dx? Sorry. So x is definitely an odd function. And we should ask ourselves, what is this integral measuring? Here's the graph of f of x equals x. On the one hand, I'm asking, what is all this area over here? Also, what is all this area over here? And both regions go off and off, on and on, however you want to think about it, forever. All right, this area over here, all the way from negative infinity up to 0, is the integral from negative infinity to 0. And this area over here is the integral from 0 to infinity. On the one hand, I want to say this is 0 because I'm integrating an odd function over a region that is symmetric about the origin. On the other hand, that area is clearly infinite. There's no chance in hell for this integral to converge. So we arrive at a dilemma. If we think about this as integral negative infinity to 0 x dx plus integral 0 to infinity x dx, both are obviously divergent. And remember, convergent and divergent, those are the adjective forms of the verbs converge and diverge. So on the one hand, I want to say it's 0 because of the symmetry. But on the other hand, it's made up of two pieces, each of which is clearly infinite in size. This is a divergent integral. This is a divergent integral because of the way we have to define improper integrals. Why is it so obvious that they're divergent? Because this region right here is all of the area underneath y equals x from 0 to infinity. So we can actually go ahead and do the computation. I'd write this as lim r to negative infinity integral r to 0 x dx plus lim s to positive infinity integral 0 to s x dx, which is x squared over 2, lim r to negative infinity, x squared over 2 from r to 0, plus lim s to positive infinity, x squared over 2 from 0 to s. And so we get lim r to negative infinity negative r squared over 2 plus lim s to positive infinity s squared over 2, which is negative infinity plus infinity. So both of these diverge. Integral 1 diverges. And the integral 2 here also diverges. So each piece is undeniably a divergent integral. And the question is, what about the original? The intuition you should have in mind here is that an integral converges if the area it measures is finite, right? If there is a definite area and that area is finite, then the integral converges. Here, the total area measured is clearly not finite. So on the one hand, I should say this integral is divergent. On the other hand, I'm going to put question marks here, or can I think of it like this? As the limit r goes to infinity, integral negative r to r of x dx. So the bottom interpretation appears to be equally valid. As r goes to infinity, this would be negative infinity to infinity, right? It looks good. But the bottom one does not line up with our intuitive idea that the integral should converge if and only if the area is finite. So this guy really would be zero, because the integral inside there is 0. So I get lim r to infinity of r squared over 2 minus r squared over 2, which is lim r to infinity of 0, which is 0. And these are two seemingly valid ways to interpret this integral. One leads to us saying the integral is divergent. The other suggests that the integral is convergent. This bottom thing here is what's called symmetric integration, where you integrate symmetrically. In other words, I'm thinking of the top bound going to infinity at the same speed I'm thinking of the bottom bound going to negative infinity. There are places where this stuff is meaningful. In fact, most of my own research involves stuff like this. Why the fuck is my email being so loud? Shut the fuck up. All right. So this bottom guy has a lot of appeal from a certain way of looking at things, but it doesn't line up with our idea that the integral should converge if and only if the area is finite, because the area here is clearly not finite. You have a piece over here that is infinite and a piece over here that is infinite. And we all know infinity minus infinity, not usually 0, right? We've seen that in Calc 1 with many of our limits there. So we're at a bit of an impasse, and this is the same problem that we had with the type 2 integral that we did at the end of class last time. You have two infinite areas, one positive, one negative. Can you conclude that they add up to 0? No, not necessarily. So I want you to think about this. This bottom way of thinking of things is valid in many circles, but not for us. The way we define convergence and the way we define improper integrals, a consequence is, here are some good things to remember. If any one part diverges, then the whole integral diverges. Because we want our definition of convergence to say the integral converges if and only if the area is finite. And this is the only way to make that work. There are other valid interpretations, and they lead to different definitions and different ways of thinking about things. But for us, if any one part of an improper integral diverges, then the whole improper integral diverges. And so this actually answers Rakib's question. You know, for the type 2 integral that we looked at last time, can't we just say by symmetry the integral should be equal to 0? Not necessarily, because if one of those pieces happens to diverge, then the symmetry doesn't matter. We should still say that the whole integral diverges. There's another way for integrals to fail to converge, and I want to look at an example like that. What happens if I try to integrate the sine function from 0 to infinity? We end up with a similar kind of issue here. We know that the sine function spends equal amounts of time above the x-axis and below the x-axis. So in some sense, I want to say that the area above the x-axis should cancel perfectly with the area below the x-axis, and hence the integral is convergent. But on the other hand, if I just follow our definition, I get something else. An antiderivative for the sine function and so I get lim r to infinity 1 minus cos r. And what is this limit? And forget about the 1 for a minute. What does cos r do as r goes to infinity? Yeah, it oscillates. Good. Gustavo, yeah, the answer to your question is yes. If you evaluate the integral and then take the limit and you get -1, then the integral converges. Morgan, Simon, and Ryan are all correct. This limit does not exist. So because the cosine function wobbles back and forth forever and ever and ever, amen, this limit right here does not exist, which means this integral diverges. Even though from an intuitive standpoint, we might want to say that it converges to 0 because the sine function spends equal amounts of time above and below the x-axis, from our definition, this integral must diverge. This is one of the things that makes this part of the class challenging, is that you really have to trust the definitions. You can't lean on your intuition so much. Infinity, very counterintuitive. There are ways of looking at this to say, yeah, this integral should be 0, and that's called measure theory. And it's totally different than the shit that would allow us than the symmetric integration from the previous example. And these are the sort of questions that slowly drove people insane around the turn of the 20th century. So remember, the definition of convergent and divergent are here. If the limit defining the integral exists and is finite, then the integral converges. Otherwise, the integral diverges. So if these limits, whatever limit you're looking at, doesn't exist or is not finite, then the integral is said to diverge. So this is a divergent improper integral. Well, the definitions are what they are. We can take issue with them, and many people have. Oh, well, computer statements and definitions, should be analogous. Definitions need to be self-consistent and clear. So defining something as the complement to something else. If this happens, we call it this. If this doesn't happen, we call it that. That's pretty normal stuff. But issues like the one we're looking at here and the one we looked at in the previous example with the integral negative infinity to infinity of x, they both hint at something kind of unsatisfying in those definitions. So for us, the easiest way to think of it is that an improper integral converges if the area it measures is finite. If you cannot necessarily say what that area is, or if that area is infinite, then we would say the integral diverges. The challenge here is that we can't really say what that area is because it depends explicitly on R. If you stop R at 10 million, or if you stop R at 10,000,001, it's not getting closer and closer and closer to anything. The area is bouncing back and forth between 0 and 1. So we end up with this oscillatory nature that depends on where you stop integrating, so you don't get the closer and closer and closer behavior that we associate with a limit existing. And indeed, the limit doesn't exist, which means the integral diverges. And this is totally consistent with our definition. So I'm not saying this to show you why our definition sucks. Our definition is great. It works really well. I'm showing you this as a break on runaway intuition. So sometimes our intuition, not as powerful as we'd like to think it is. And we need to fall back on our definitions and on our reasoning, our very, very careful reasoning. So what Simon's talking about in the chat there is not directly related to this, but there is something like that. The uncertainty principle and superposition, wave function collapse are issues in quantum physics that have to do with observing something affecting its state. You could maybe think of like a choice of R as being an observation, but I would hesitate to try and relate those two because I don't see an immediate relationship. What I do want to do is play around a little bit more with your comparison test, because the comparison test for improper integrals is similar to some tests we're going to use for series later, and I think it will be helpful to get a little bit more comfy. So let's examine the integrals. Let me do it like this, actually. Objective collapse model. I'm actually not a fan of wave function collapse. I'm a many worlds guy, but I'll take a look at it. So that first integral is interesting. I don't claim to be able to find the value of this integral, but I do claim that I can tell you that that integral converges. Can anybody help me come up with an argument showing why this integral might converge. Oh, and I left off my dx, sorry. So remember, going to 0 on its own isn't enough. We can't pull the x squared out. So remember, 1 over x goes to 0, right? But the integral of 1 over x diverges. So going to 0 isn't enough. You could split it the way Simon is suggesting there. And then the 1 over x squared piece we could handle, but the sine x over x squared piece we could not. Because we'd never find an antiderivative. That is a function for which there is no closed form antiderivative. But we're getting closer. Does anybody remember the two different ways we talked about the integral of 1 over 1 plus x squared last time? That guy we were able to evaluate directly. But then we also were able to look at him using our comparison theorem. So if I'm able to build an inequality here, relating this function to another function whose integral's convergence is known, I might be able to get some good information out of that. We know that -1 is less than or equal to sine x is less than or equal to 1 for all x, right? Sine is always bounded between -1 and 1, which means 0 is less than or equal to sine x plus 1 is less than or equal to 2. And in turn, 0 is less than or equal to sine x plus 1 over x squared is less than or equal to 2 over x squared. And this is all true, for all x, for all real numbers x. Moreover, the integral from 1 to infinity of 2 over x squared dx is 2 times the integral from 1 to infinity of 1 over x squared dx. And this has a special name. What kind of integral is that? Yeah, it's similar to the squeeze theorem. Remember, I'm going to be leaning on our comparison theorem for improper integrals, which is a consequence really of the squeeze theorem. But this integral right here, 1 over x squared dx, that's a special kind of integral. What kind of integral is that? Has a name. We talked about it on Wednesday. Yeah, it's a p integral. Here, p is equal to 2, which is bigger than 1. So this integral is convergent. And I want you to notice that I was very careful here. the integral 2 over x squared from 1 to infinity is not a p integral. The 2 fucks it up. The integral 1 over x squared from 1 to infinity is a p integral. Because this guy is a convergent p integral, the one with the 2 inside, which we know is just 2 times that, must also converge. Therefore, by this inequality, which I'll label star, and the comparison theorem for improper integrals integral 1 to infinity sine x plus 1 over x squared dx must converge. And I want you to pay attention to every little bit here, especially the words and the logic. You will be making a lot of arguments like this, and you need to get to a place where you're comfy writing sentences like this, referring to and building inequalities like this, remembering previous theorems like this. This is a problem that feels a lot like the majority of the problems that we'll be doing for the next several weeks. Sequences and series will feel similar to this. Any questions on how I was able to conclude that the first integral here converges? If the bounds were different, we may or may not be able to use that reasoning. If this bound was a 0, then I could not use that reasoning because this is no longer a type 1 integral, because the 0 here, this guy has a problem at 0, right? He blows up at 0. If this was a 2 or a 3 or a pi or any other positive number, we would be okay, and we could use the exact same reasoning. But if this were a 0 or any negative number, any number such that the interval from that number to infinity included 0 or any other place where this function has an infinite discontinuity, then I could not make use of that. So the thing that this hinged on was this inequality and the fact that this integral is convergent. The reason I know that this integral is convergent is because it's a p integral. And remember, p integrals are any integral of the form a to infinity 1 over x to the p. Yeah, that's exactly right, Nicholas. So the calculation stuff is really not the core of mathematics. The core of mathematics is proving theorems. And the way we prove theorems is with other theorems. So it's very much a logic game. Any questions about what was said here or how we said it, why we said it that way? Okay, let's, oh, yep, sorry. The comparison theorem for improper integrals says if 0 is less than or equal to f of x is less than or equal to g of x, then the integral from a to infinity of g of x converging implies the integral from a to infinity of f of x converges. And if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity of g of x diverges. So this should be in our notes from the other day. Here, f and g are assumed to be continuous. So you're definitely only dealing with type 1 integrals. It says, if you fit in a finite box, then you are finite. And conversely, if an infinite box fits inside you, then you are infinite. So let's look at the second problem I had there. What about the integral from 0 to pi over 2 of secant squared? What can be said about this guy? The comparison theorem, it's not directly dependent on the squeeze theorem, no, but the easiest way to prove it is via the squeeze theorem. Yeah, the limits that you would establish to prove this can be thought of as consequences of the squeeze theorem, but really this is a little bit heavier than the squeeze theorem. Okay, so any thoughts on how to attack the integral on the screen now, the 0 to pi over 2 secant squared integral? First, is this integral improper? Good, yeah, it's a type 2 integral. It is improper. It's not type 1. There's no infinities in the limits here, in the bounds. But remember, secant squared, just like secant, he has vertical asymptotes all over the place, and one of them is pi over 2. So I'm looking for the area from 0 to pi over 2. That's this region in here, all this stuff. So this is indeed an improper integral. It's a type 2 improper integral because we have a problem at pi over 2. Yeah, no infinite discontinuity at 0. Secant of 0 is 1, no problems there. But we do need to treat this upper bound with some care. So I would write this as the limit as r approaches pi over 2 from the left. All right, think about our graph here. I want to sneak up on this infinite discontinuity. And the way to do that is to come in from 0 here and sneak up on it from the left. And then integral 0 to r, secant squared x dx. Now, secant squared is easy to find an antiderivative for, so I don't need to futz about with any comparison theorem here. I can do the work directly. Antiderivative for secant squared is tangent. So that's the limit as r approaches pi over 2 from the left of tan r minus tan 0, which is 0. What does tangent do as you sneak up on pi over 2 from the left? Yeah, he blows up. He blows up to plus infinity because the graph of tangent, remember, from negative pi over 2 to pi over 2 looks like this. So if I sneak up on pi over 2 from the left, that means I'm walking up here. So I'm going up to plus infinity. So trig functions can also yield fun improper integrals. Yeah, very good. So this, and it's integral 0 to pi over 2 secant squared x dx diverges. There's plenty of other fun games we can play. I don't want to bore you. I think, is there anything else here that I'm fucking up? Oh yeah. It's a good time to introduce the gamma function. Talk about Mellin transforms. I guess we'll talk about the gamma function real quick. So one of the problems that I put in your homework this week is actually a problem that I put on the final exam for Calc 2 a couple semesters ago. And then I feared for my life for about a week because I thought people might come and try to kill me. So I won't put it on your final, but I did put it in your homework. I want to talk about the factorial. Of an integer n. Here's the definition. We use the exclamation mark for the factorial, and n factorial is defined for us to be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. For example, 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 is 720. So this is the definition of the factorial function. But you may notice this definition doesn't work so well if n isn't a whole number. So the way you find the factorial of an integer is you multiply that number times that number minus 1 times that number minus 2 times that number minus 3 all the way until you get to 1. But if the number you start with isn't a whole number, then you're never going to land at 1 by subtracting whole numbers and multiplying all of them. So one of the big questions in mathematics around the 1500s was, how do you extend this definition to apply to numbers that are not whole numbers? There's more than one correct answer. There are things called rising and falling factorials, which will allow you to get there. But the smartest mathematician to exist in that time, Leonhard Euler, came up with a really sneaky way to do it. I guess he was a little bit later, 1700s maybe. Anyway, Euler came up with another way to do this, called the gamma function. So if for some reason computing a big improper integral is easier than multiplying these things, Euler noticed that if you plug in a positive integer n, make sure I get this right, to this formula, it will also yield n factorial. All right. Yeah. So what I would like to do is to show you that this really works, at least for a few values of n. And then one of your homework problems is to prove that it always works. And what's neat is that this guy, you can plug in things that are not whole numbers for n and it still works. And that allows you to extend the definition of the factorial function to arbitrary, real, and even complex numbers. The factorial function is hugely important in counting problems. Anybody who's taken statistics already knows this. It's the number of permutations of an n object set. So if I wanted to ask how many different ways can I stand you guys, assuming we actually had a class here and I had like 30 of you, how many different ways can I arrange you guys in a line? That would come from n factorial. If I wanted to ask how many ways can I arrange you in a circle, that would be n minus 1 factorial. So 30 or 29 factorial respectively. Counting problems, combinatorics problems, problems that have to do with how many ways you can arrange things. Factorials show up quite a bit. Also very important in number theory. So let's see. Can we show that integral 0 to infinity x to the n e to the minus x dx equals n factorial for n equals, let's do like 1, 3, and 5, say, or maybe in general. Let's check n equals 1. Integral from 0 to infinity, x to the 1, e to the minus x dx. That's the limit as r goes to infinity. Integral 0 to r, x e to the negative x dx. How do we do this integral? It is fun. Yeah, this is good shit. Yeah, good. This is an IVP problem. So here I'll pick u to be my polynomial following the Lipet rule, and dv to be everything else. That's e to the negative x dx. du is then just 1 dx, and v is negative e to the negative x. So I have some IVP going on inside my improper integral. That gives me lim r to infinity, and I'm going to open up big parentheses. This is a definite integral, so I need to remember to evaluate. I'll have negative x e to the negative x evaluated from 0 to r minus the integral from 0 to r, negative e to the negative x dx. Now that first piece, I can evaluate between bounds. When I plug in r, I get negative r e to the negative r. When I plug in 0, I get 0, so that goes away. The two minuses here will make a plus, integral 0 to r e to the negative x dx, like this. That's the same as the limit as r goes to infinity, negative r over e to the r, plus, then this piece becomes negative e to the negative x evaluated from 0 to r. Here, if I do the evaluation, I get negative e to the negative r minus negative e to the negative 0. So that's negative r over e to the r plus 1 minus 1 over e to the r, like so. And then I split that limit up. So I'll have negative lim r to infinity r over e to the r plus 1 minus lim r to infinity 1 over e to the r, like so. What is this? As r goes to infinity, where does e to the r go? Yeah, e to the r, this piece down here goes to infinity. So this is 1 over infinity. This is 0. What about this guy? How do I send r to infinity in this expression? The top and the bottom both look like infinity over infinity. L'Hopital's rule, very good. So I'm going to come off to the side here and do a little L'Hopital calculation. This looks like infinity over infinity, so we need L'Hopital's rule. So by L'Hopital's rule, that's equal to the limit as r goes to infinity of 1 over e to the r, because the derivative of the top is 1, the derivative of the bottom is e to the r, and that's the guy we just said is 0. So this is 0 as well, which means this whole thing is equal to 1. And 1 is 1 factorial. So at least for n equals 1, this works great. And the question is, can you show that it works in general? The procedure is the same thing, except you'll need n applications of integration by parts rather than 1 application of integration by parts. So I want to give you a hint for that homework problem. N factorial, which we said is n times n minus 1 times n minus 2 times all the way down to 3 times 2 times 1. Looks like that. What about n minus 1 factorial? Well, the factorial of anything is that thing times that thing minus 1 times that thing minus 2 until you get all the way down to 1. We want to look back at this page for a second. This page. Yeah, here, I'll leave it here for just a sec. Yeah, no problem, no problem. So we do some IBP, and that lands us here after we do the algebra and evaluation. All right, this is the original IBP output. I evaluate the first piece to this. I clean up the second piece to this. Then from here to here, I just evaluate an antiderivative. Between bounds, it looks like that. And then I take my limits. And since these pieces both go to 0, the total output is 1. So this guy, let's do it here. Negative e to the negative x evaluated from 0 to r. That's equal to negative e to the negative 0 minus negative e to the negative r, which is negative 1. E to the 0 is 1. So negative e to the negative 0, that's the same as e to the 0. That's negative e to the negative 0 is negative e to the 0 is negative 1. And then this is plus e to the negative r. And that's the same as e to the negative r minus 1. Oh, did I swap that around? What did I do here? Oh, I did swap that around. I'm sorry. Shit. That's not going to help unconfuse things. That's going to make it worse. Here, I'll do it here. So this piece, negative e to the negative r from 0 to r, that's the same as negative e to the negative r minus negative e to the negative 0, which is negative e to the negative r plus e to the negative 0, which is negative e to the negative r plus 1, or 1 minus e to the negative r. So this piece is this piece. L'Hopital's rule says if you're trying to take a limit and it looks like infinity over infinity or 0 over 0, then you can differentiate the top and the bottom separately and try again. Yeah, so the derivative of the top is 1, the derivative of the bottom is e to the r. So one application of L'Hopital's rule turns this into this, and this guy I know goes to 0 as r goes to infinity. Okay. So I want to return to this little bit that will help you on your homework problem. If n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1, what the hell is n minus 1 factorial? Well, anything factorial is that thing times that thing minus 1 all the way down to 3 times 2 times 1. So this is n minus 1 times n minus 2 times dot, 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 all the way down to 3 times 2 times 1. And what you notice is that this piece of n factorial is n minus 1 factorial. And that yields what's called a functional equation, or a recursion. N factorial is equal to n times the factorial of n minus 1. And that's the easiest way to prove that that integral does what it should do. So you want to show that integral 0 to infinity x to the n e to the minus x dx is equal to n times integral 0 to infinity x to the n minus 1 e to the minus x dx. This is what you want to show on that homework problem. And the way you get there is integration by parts and L'Hopital's rule. It's broken down into steps, and WebAssign will kind of hold your hand through it. I don't think you'll have a hard time with it, but I wanted to give you these little bits of things because they're a lot of fun. What we're getting at here is something that's kind of a big deal in differential equations. If you take a function, multiply it by e to the negative x, and then integrate from x equals 0 to x equals infinity, what you're really doing is calculating the Laplace transform of that function. And integral transforms are a huge important part of information theory. Really an important part of a lot of different things, functional analysis. But this particular one is called the gamma function. So gamma of s is the integral from 0 to infinity x to the s minus 1 times e to the minus x dx. And this is the function that Euler invented. It's very, very similar, you see, to the function above, only we've got s minus 1 instead of s, or s minus 1 instead of n, right? X to the n here, x to the s minus 1 here. This is called the gamma function. And he shows up in all sorts of weird and surprising places, in number theory and different bits of analysis. And he's a lot of fun. That is really it for section 7.8, guys. I don't have anything more to teach you when it comes to this stuff. You just gotta practice with it. I think maybe we'll do 1 or 2 more practice problems, but I don't want to jump ahead into section 11.1 just yet. Fuck it, maybe we should. Here we go, I got an idea. If you know the answer to this question, please don't spoil it. I.e., let's refrain from typing the answer in chat. The factorial function is a function whose domain is just the whole numbers, right? In fact, it can only take non-negative. Takes only non-negative whole numbers as its input. Such a function is called a sequence. So a function whose inputs are positive whole numbers or non-negative whole numbers are sequences. That's all. That's the definition of a sequence. We know that, maybe I'll call it capital F or lowercase f, n, for n factorial. This is the notation we usually use for sequences. We know that f1 is 1 factorial is 1, f2 is 2 factorial is 2, f3 is 3 factorial is 6, f4 is 4 factorial is 24, and so on. Would anybody care to conjecture what f0 is? Or does anybody see a pattern that allows me to go from f4 to f3, from f3 to f2, from f2 to f1? If I take f4, that is 4 factorial, and I divide it by 4, I get 6, which is f3. If I take f3 and I divide it by 3, that's 6 divided by 3, that's 2, which is f2. So if I take f2 and divide it by 2, I expect to get f1. Let's see, well, that's 2 divided by 2, that's 1. Yeah, that is f1. So what should happen if I divide f1 by 1? I see, I'm sorry, my internet must have been fucking up. Are we back? Okay, good. So notice if you divide fn by n, you get fn minus 1. So f1 divided by 1, that's 1 over 1. This should be equal to f0. In other words, zero factorial is also 1. And this is something that people tend to have a hard time wrapping their heads around intuitively. There's a few other ways to think about it. But this is maybe where we'll end with this definition of a sequence. We're going to talk a lot more about sequences starting next week when we move to chapter 11. So after 7.8, we go to 11.1. We will spend about a whole week on sequences, and then we'll spend several weeks on series. There are a bunch of theorems on sequences. I'm going to pull up your textbook here. So this is where we're going next week. Sequences and series. And there's a lot of notation and stuff that you're going to have to get used to. We'll talk about it, but the notation is like what I was using there for the factorial. A handful of definitions, what it means for a sequence to converge. But then we have a bunch of theorems, right? This, these guys, this stuff, this stuff. So next week is going to be very theory heavy. Simon, reach out to me through email for that. So I would recommend, if you happen to finish this week's homework early, and do make sure you finish this week's homework, it's hugely important, that you go ahead and start reading section 11.1. There's a lot to read here. There's a lot of definitions, there's a lot of theorems, and some of it is a little bit hard to understand. So the better head start you can give yourself, the easier this will be. There's some notation, which is the notation that I was just introducing, and definitions, what is a sequence. But beyond that, there's a lot to talk about when it comes to convergence or divergence of a sequence. And you need to understand 11.1 to have a chance at 11.2. And it is sections 11.2 through 11.11 that give this class the reputation it has for being a hard class. Sequences and series, that's the stuff that people really struggle with. So I'm going to finish up here, I guess a little bit early today, which is fine, with that warning that we're approaching what is really the hardest stuff in this class. 7.8 is a great introduction to convergence because it talks about stuff that we know. It talks about limits and integrals, which are things that we're familiar with, and then it introduces this language of convergence and divergence in that setting. But the more natural setting for that stuff is sequences and series, and that is where we will be going starting Monday of next week. So please, if you haven't seen Wednesday's video, make sure you watch that and watch it carefully. We talk a lot about the definition of convergence and divergence for improper integrals. Make sure that you've digested the things we've talked about here today, especially the improper integral things. This is fun. The factorial stuff is fun. but stuff like this is very important. So remember, if any part of an improper integral diverges, the whole improper integral diverges. And that we can handle improper integrals reasonably well as long as we remember to write them first as limits of proper integrals, and you need to be comfy writing them as limits of proper integrals. Right now, I have the homework set up to be due on Monday. I know that gives you a little bit less time to work on it than we would otherwise. I'm happy to extend if need be, but I would like you to try and get it done by Monday so that we can move on to the material in chapter 11. We lost a little bit of time having to push the exam back, and this is a good place to make that time up because the section isn't especially challenging. But of course, if you do end up needing more time, I would be happy to extend. So please try to get that homework knocked out over the weekend. If you need more time after Monday, just submit an extension request and I'll happily grant it. And yeah, that is it. That is where I'm going to leave things for today. If you want to talk to me, you can send me an email or come by my office hour. I will have my normal office hour today from 1 to 2. And I'll do my best to get your exams all graded and sorted out by Monday. All right. Any last minute questions for me before we shut things down here? Okay. Now, Ryan, I see you wanted the notes. I actually have to go run and grab my wife from work real quick. So what I'll do is I'll scan them and send them to you through email or Canvas. I will have my office hour today, but it's going to be a little bit rushed. So I just want to be a little bit more efficient there. All right. I hope you guys have a lovely weekend. Work hard on that homework. Try to get it all done by Monday, and we will move forwards from there. Take care, guys.